For the scientific graphing activity, we are drawing graphs. We are coming up with the linear relationship from the graph, and we're writing the equation for the linear relationship. We have some data here, which is for a sphere. It is radius and the corresponding surface area. So the table shows us the data. And a graph is made of surface area on the y-axis versus radius on the x-axis. Notice that the graph is titled. We can title it any number of ways. One simple way is whatever's on the y-axis versus whatever's on the x-axis. So surface area versus radius of sphere. And notice that we label what the axes are, surface area and radius, and we also give units. Centimeters squared for surface area, radius has units of centimeters. So we need all that information. And the graph is not linear, and it has an appearance to it of kind of like a y equals x squared sort of relationship. Well, it turns out that that's what the relationship is. So if we take all those radius data, 1.5, 3.0, etc., and we square them, we end up with 2.3, 9.0, 16, etc. Keeping the surface area the same, we make a new graph. Now it's surface area as before, but versus radius squared. Notice we have to retitle our graph, surface area versus radius of the sphere squared. Well, it looks linear, so we fit it with a linear function, and we get a slope of 12.6 and a y-intercept of 0. So remember that a linear graph abides by the equation y equals mx plus b. We found from the fit that m, the slope, is 12.6, and the y-intercept b is 0, so we can write that equation for this relationship, y equals 12.6x. But then we replace y with what it is, surface area, and x with what it is, radius squared. Really pay attention to that. It is not just radius, it is radius squared. And then we can apply that because that equation will work for any sphere like that of the Earth. We have the radius of the Earth. It is 3,959 miles. Maybe on the average. We square that, multiply by 12.6, and we get the surface area of the Earth. That's that value, 1.97 times 10 to the 8th miles squared. The nonlinear relationships that we're going to work with today are y equals 1 over x, y equals x squared, as we just did work with, and y equals 1 over x squared. So notice that if we are given data, we make a graph of it, and it looks like the first graph, well, then it could be a 1 over x kind of relationship. If, on the other hand, it looks like the second graph, then for our data today, it will be an x squared kind of relationship. If it looks like the third graph, which I agree with you looks a lot like the first graph, then it's that 1 over x squared kind of relationship. So here's some data, and there's lots of stuff shown. What we should pay attention to is the second column, surface temperature in Kelvin, and we see those high numbers because we're talking something very hot, and the wavelength. So we have data. It's those middle two columns, surface area, surface temp in units of Kelvin, and wavelength in units of nanometers. Wavelength is a length and nanometer is a length. So we make a graph of that data, putting the wavelength on the y-axis and temperature on the x-axis, and that is the graph we see on the left. Well, it's not a linear relationship. It's one of those two graphs we had from above here. It's either the first or the third graph. It turns out it's the first graph. It's a 1 over x relationship. So the fourth column in our table up there is the temperature in Kelvin inversed. So inverse temperature, we have to inverse the unit. It's now 1 over Kelvin. So if we take the inverse of 1.5 times 10 to the third on our calculator, we end up with 0.000667 and so on. So we take all the inverses of those temperatures. Now we make a new graph, keeping the y-axis the same, still wavelength, and the x-axis is now inverse temperature. Notice the unit 1 over Kelvin. Well, we have a linear relationship. Now what we want to do is determine what the slope is. In the example we looked at above, we were given the slope. Well, let's see how we would calculate it, just as you would have done in a math class. The slope is the rise over the run, delta y over delta x, or y2 minus y1 over x2 minus x1. So what we do, and here's the graph again in more detail, what we do is we get out a ruler, we draw the best straight line through our data, not favoring any data point, just trying to eyeball it and drawing the best line through it. And then we choose two points that are on our line. They could be data points if they're right on our line, or they're just other points. The points used in this analysis are the points x1, y1, 0.000140, 400, and x2, y2, 0.000600, 1800. So using those data points, we calculate the slope. So y2 minus y1, 1800 minus 400 divided by x2 minus x1, 0.000600 minus 0.000140. We put units in there, and for the y, it's the y units, nanometer. For the x, it's the x unit, 1 over Kelvin. So when we take that difference, do the division, we get 3.04 times 10 to the 6th. Notice our units are simplified, nanometers, Kelvin. The next part is to determine the y-intercept value, the value of b. So in step 3, we see that we can write the equation now as y equals the slope, 3.04 times 10 to the 6th times x plus b. Well, we have to find the value of b, so we take a point, and we put in the value for that point of y and the value for that point for x, and we solve for b. So we have y 400, x 0.000140, and we just do that algebra there, and we find b has the value negative 26. So now we have the slope, we have the y-intercept, so y equals the slope, x minus 26, but what we do is we replace what y is with what it actually is, wavelength, x, what it actually is, 1 over t. So then we have wavelength equals 3.04 times 10 to the 6th, 1 over t minus 26. So when you in the activity write out the equations, be sure you replace y with what it physically is and x with what it physically is, however it's been altered. Alrighty, so here are some instructions on your graph, and you may use any graph paper. You give it a title. Often it's just whatever y is versus whatever x is. Make sure you use the majority of the graph space as you can. Label the increments, label the variable, and give units. So you're labeling what the y-axis is, what its units are, the x-axis and its units, and draw the best fit line, and so forth. You may skip the pre-activity as usual, and here's the report that you'll be filling out and then scanning and turning in. So here's some data, mass and radius. And the graph is already drawn for you. The slope and y-intercept are given. You're asked to write out the equation. Now, don't write y or x in your equation. Write what y is, radius, what x is, mass. Put in the value of the slope, put in the value of the y-intercept. You're also asked to think about what the units are for the slope and the y-intercept. So go back through that example above if you need to. Here we're given data. This is distance and acceleration data. The graph is made of just acceleration versus distance. We see it's not linear. It turns out to be a 1 over x squared kind of relationship. So the distance data were inversed and were squared. A new graph was made, and that's the second graph. The slope and y-intercept have been calculated for you. So once again, you write out the equation. Remember to use the term acceleration in it. Use the term distance. Of course, you're going to have 1 over distance squared. You'll determine the units of the slope and the y-intercept. Alrighty, and then now you're going to be generating graphs, and that's where you use graph paper to make those graphs. Don't forget all the information needed for the graph. And we are given concentration and rate data, and a graph was already made for us of rate versus concentration. It is not linear. What graph type does it look like? So remember those 3 choices, 1 over x, x squared, or 1 over x squared. So determine which one it is and alter the x data, alter the concentration data. That's what the first blank column of the table is set up for you. So if it's, for example, concentration squared, that's what your label would be for that column. Of course, then you would have m squared. The m turns out to be molarity. You then have your graph and you fit it with a linear line and you calculate the slope based on points on that line, and that's what you write in this calculation of slope space. You calculate the value of the y-intercept. M equals B equals, that's where you put the actual numerical value, include the units for the slope and the y-intercept, and then write out your equation. Don't have y and x in it, have the rate in it, have the concentration, and however you altered it in there. And then you're doing that same thing again with this data, which is acceleration and mass data. And you see that the graph is not linear to start with, acceleration versus mass. So think about how the mass has to be altered, either inversed, squared, or inversed and squared. And then you make the graph and you calculate the slope, including units, calculate the y-intercept, include units when you write out finally the numerical value, and then write out your equation. Once again, the equation needs to involve acceleration and mass, however you've altered those. And of course, the value of the y-intercept, the value of the slope. Alrighty, so when you're done with that, do a double check on it and scan it, prepare the PDF file, and then submit it.